Welcome everyone to the Osmocom developer call tonight. The topic is the GSMA IoT eSIM, especially comparing it to the consumer eSIM architecture. These relevant specifications are SGP 3132. This is a relatively new set of specifications. It has been around maybe for, I don't know, 1.5 years, maybe around that. And to my knowledge, there are no commercially deployed systems yet, but we are about to see the first ones showing up. And that's a good opportunity to look at what's going on. So I have a couple of slides through which I'm trying to get relatively quickly, because they just recap the consumer eSIM to just remind us about the background. If you want to revisit those later, there was other talks that cover this in more detail, but as I said, a very quick reminder. So, well, a classic SIM card was introduced in the 2G GSM cellular system, first deployed in 1991. SIM stands for Subscriber Identity Module. It was a single-purpose smart card, and the fundamental purpose is, well, mostly the holding the secret shared key material that is used for cryptographically authenticating the subscriber and also for generating the encryption keys over the interface. There's also some other information stored. Then later on, a decade later, when UMTS or WCDMAs, like our North American friends tend to call it, was specified and deployed, there was something called the UICC and the USIM that decoupled the card from the USIM application. USIM stands for UMTS, Subscriber Identity Module. The purpose is still the same, just a couple of additional parameters and different authentication mechanism and so on. And then finally, last but not least, the eSIM came around, which is a virtualization of the USIM. And it decouples the SIM profile, so let's say the logical content of this subscriber identity module from the physical chip. So that chip is now called EUICC, and the EUICC can hold one or more SIM profiles. And the SIM profile then is the virtualized SIM card. It contains anything that the SIM or the USIM contained previously. And to enable this and to make this work across multiple different vendors, there are different specifications. The format of the eSIM is specified in the so-called EUICC profile package specification by the Trusted Connectivity Alliance. And the actual transport and download and authentication and so on of such an eSIM profile into the EUICC is specified by GSMA. Well, we won't have a demo time here. It's specified by GSMA, and there's 3 different GSMA systems. We'll just talk about that in a couple of slides later. So the EUICC itself is a smart card chip. It has some additional security requirements compared to the classic SIM or UICC. But fundamentally, it's still a cryptographic smart card chip that speaks the same electrical interface and the same transport protocol to the phone or the cellular modem, cellular baseband chip, as a classic SIM card. There's no change on that. It's just, let's say, different contents and different applications and so on the EUICC. Yeah, so on such an EUICC, we have various different things, most notably the EUICC operating system, and on top so-called profiles. Here in this example, we have one enabled profile of one mobile network operator, and we have another profile that's disabled. In classic version 2.x eSIM universe, there can only be one enabled profile. In version 3.x of the eSIM specification, there is something called MEP, multiple enabled profile, that allows multiple profiles to be enabled at the same time. That is basically meant to resemble the multi-SIM, dual SIM, for example, capabilities in the physical SIM universe. Those multiple enabled profiles share still one physical interface. So it's not like there are two, like this, if you have a dual SIM phone, you have two different SIM cards and two different electrical interfaces to those cards. But in the MEP enabled EUICC, you only have one physical interface and then some multiplexing going on a protocol level. Yeah, so that gets us to the three eSIM flavors. We have the so-called M2M eSIM that was released first. It's specified in SGP 0102. And the consumer eSIM specified in SGP 2122. And the IoT eSIM specified in SGP 3132. So you can see a clear pattern there. 10, 20, 30 designates the flavor of the eSIM. And then we have the ending digit in 1 is the overall architecture, and the ending digit in 2 specifies the actual protocol and data formats and so on, and procedures. If we look at the consumer model, which is well, let's stay here quickly. The machine-to-machine eSIM has virtually nothing to do with the consumer eSIM. Those are completely different systems with completely different protocols and network elements. The only thing that's the same, I think, is the format, the data format, how you describe the actual profile, the Trusted Connectivity Alliance interoperable profile format. But everything else is completely different. And so we'll not look at this here in this context, but we'll look at the consumer eSIM and compare it to the new IoT eSIM and check what the differences are between those. In the consumer model, that's the diagram from the spec. It looks rather complex, but we can ignore a lot of it to simplify it. So in the end, we have the EUICC here, the chip onto which the profiles are installed. And we have on the top side the SMTP Plus. That's the Subscription Manager Data Preparation Plus. This entity, the SMTP Plus, is where the eSIM profile gets personalized. Personalization means the subscriber-specific parameters get inserted into the profile template. So the IMSI, the key material, and so on, and all the cryptographic, the profile protection, so-called profile protection and profile binding, and so on, all happens in here. And then once this is all cryptographically wrapped up over multiple layers of secure channels, this is downloaded into the EUICC. And in order to do that, we have some software on the phone or the device. That's an LPA. Here, the sort of whatever yellow-ish block with the dashed line. And the LPA is a piece of software that on the one hand side talks to the EUICC, and on the other hand side it talks to the SMTP Plus. And it also has the LUI, the local user interface. That's basically if you have a smartphone and you select a specific eSIM to be enabled, or you download a new eSIM, that's the local user interface that takes care of that. So it's just different logical functions within this software. There's some other elements, but we can ignore them for now. So this is just the important parts in the consumer eSIM, the EUICC, the LPA, and the SMTP Plus. Now, of course, that SMTP Plus needs to get its data from some operator and so on, but that's another detail. So we have this LPA software, the local profile assistant, on the client device. I already mentioned that. SMTP Plus, I also explained that already. Maybe quickly go a bit in detail what the SMTP Plus does. It generates the profile package by personalization, then that gets protected, means cryptographically encrypted. Then it gets bound to a specific EUICC, meaning that only this one EUICC can decrypt the profile, and no other EUICC can do that. Then it stores those profile packages, it delivers them during the download process, and some other functionalities associated with that. We skip some more slides here. We can also skip that. The ES9 Plus maybe is worth mentioning. So that's the interface. Actually, that's wrong. It's the interface between the SMTP Plus and the LPA. Just a copy and paste error here, my apologies. So this should mean LPA on the slide here. It's an HTTPS-based interface. So basically your LPA software in the smartphone or in your embedded device establishes an HTTPS connection to the SMTP Plus with normal TLS certificate authentication, and basically the client, the LPA, verifies the TLS certificate as the server, like you would have in a normal web browser situation. And then there is two flavors of protocols, so-called JSON or ASN1 bindings. The spec says both are mandatory. In reality, I haven't seen any SMTP Plus that implements the ASN1 binding, sadly. So in reality, it's always JSON, but it's the most exciting protocol stack that GSMA could come up with, because basically it's always ASN1 distinguished encoding rules, binary data that then gets base 64 encoded into text, and that base 64 text gets put into JSON, and that JSON gets put into HTTP, and that goes into TLS, and that goes into TCP/IP. So yeah. So it's rather complex. That's sort of the message I want to get across. And that's something, of course, in IoT devices that needs some simplification, which we will get to when we look at the IoT, EOICC, and eSIM. Yeah, so we skipped the certificate chain, the compliance, and so on. We look very quickly at the consumer eSIM download, how that looks like. So basically the end user makes some kind of contract with a mobile operator, and the mobile operator orders basically the creation of an eSIM profile at the SMTP Plus that gets confirmed back and forth, and at some point the operator basically activates that subscription. And at this point in the SMTP Plus, the eSIM profile can be downloaded. And as part of this process also, the so-called matching ID was communicated. The matching ID is what ends up in your QR code for eSIM download. And then that matching ID basically acts as a token. If some customer contacts the SMTP Plus and presents that token, the SMTP Plus knows which eSIM profile this is all about. The actual download then looks like this. So we have the LPA that first talks to the SMTP Plus. It performs the common mutual authentication. It's a cryptographic mutual authentication using elliptic curve cryptography and X509 certificates on both sides. So spare you the details here. And then after that proceeds, the actual download is this profile metadata is communicated, and the actual download is done between those elements, and finally also the download confirmed between those two. Spare the details of that. So let's just very quickly the download profile enabling. Maybe look at that very quickly. So enabling or disabling a profile is something that is entirely local to the device. There is no network connectivity required, and no SMTP Plus or any other server-side element involved. So it's only the end user interacting with the local user interface. And then this triggers some commands to the EOICC, and that then gets basically acknowledged or not by the EOICC. And then there's, let's say, if the profile change was successful, then the EOICC also needs to tell the baseband processor that basically all the contents of all the files have changed, new IMSI and so on, new configuration, everything is different, new keys. So a refresh command gets set to the baseband operating system, which then starts to reread the contents of the SIM, of the eSIM profile in this case, and then executes the network attached profile with the new profile that was enabled. But again, it's all entirely local, and the decision of what profile to enable or not is something done by the local user in front of the device. I'm focusing on that to contrast it with the IoT EOICC, to which we get now. So that IoT eSIM RSP is remote SIM provisioning, is heavily based on the consumer system, and it provides more control for the IoT device owner. Now, of course, you can put a consumer eSIM profile and a consumer eUICC in your IoT device if you build one. There's nothing that prevents you from doing that. But the problem sort of is that the system is designed in a way that there's a local user that decides what download to make and what profile to enable or disable. Now, of course, you can adjust the software and control those things remotely from some central server instead of a local user interface, and then you're sort of getting into the what the IoT eSIM does. But what you cannot do while you use the consumer eSIM is to have the same cryptographic security guarantees. So, for example, your device could be hacked, and a local attacker on the device could enable or disable a different profile. All these kinds of things, because the control of the consumer eUICC is given to basically the person in front of the device, and that's something you normally don't want in a lot of IoT devices. So the control is basically taken remotely and not local to the device anymore. And in contrast to the sort of the same situation already with the centralized control existed in the M2M eUICC, but in the M2M scheme, the problem is that it's really only useful for large deployments of devices, and you cannot use the same consumer eSIM profiles, so you need some special subscription with operators that provide you these machine-to-machine eSIM profiles, and it's not as easy to switch between operators, and it's difficult to deploy different eSIM profiles of different operators onto your fleet of M2M eUICCs in that old scheme. And in this new IoT eSIM scheme, you as somebody who operates a fleet of IoT devices, even in a very small number of IoT devices, in my example here, 4 devices, and each of them in a different, receiving an eSIM profile from a different operator. You could do that very much in this IoT eSIM system. Because the control is fully with you and not so much with some provider or So what has happened is that the LPA, the local profile assistant of the consumer eSIM, has been split in half. The lower half becomes what's called the IPA. It's not the Indian Pale A and not the IP access multiplex protocol. It's the IoT profile assistant. So that's the successor of the LPA on the device, and the upper half of this, what used to be the LPA, becomes the EIM, the what was it? The eSIM IoT manager. No, I forgot the acronym. My apologies. Happens to me. That's a server-based component, and the control basically of what to download or what to enable, disable moves to this EIM, the centralized server component, and the eUICC, the chip itself, is extended with capabilities to provide authenticated, enable, disable, and profile delete and so on, which is not the case in the consumer eSIM. So the profile enable, disable, and delete are local commands issued by the local user interface, and there's no cryptographic authentication that the eUICC has performed it. It just sends an OK, but that OK could be spoofed or manipulated or whatnot. But in the IoT eSIM, that has changed. So if we look at the architecture, it actually looks a bit simpler, but it's just because they didn't include all the things from the other diagram. In the consumer domain. So we still have the eUICC, and they explain the eUICC internally has different security domains, but we can ignore this for this discussion. So we have the eUICC that's in the device. We have the IPA as the replacement of the LPA in the device. And we still have the SMTP Plus that provides the profiles. But in between, we have the eSIM IoT remote manager. Now we know what EIM stands for again. I couldn't remember it just a second ago. So the EIM is an element here in between the IPA and the SMTP+. We can see there's also a direct path. We'll talk about that later. So yeah, what has happened to get us from LPA to IPA in the device? We get rid of the local user interface because most often there is no local user. Even if there is one, let's say it's a Coke machine, there is a user interface, but and there's a user interface, but clearly the person buying a Coke should not be defining what kind of cellular connectivity that Coke machine has. So that's not the place where you want to have a user interface for eSIM deployment. And it introduces a new interface called the ESIPA interface. We see it here, the interface between the EIM and the IPA. We'll talk about that interface in more detail shortly. It adds a couple of extra ES10X functions. ES10 is the interface here between the IPA and the EU ICC. Those are related to the new functionality. I'm not going to read all those operations here. We look at that. And the LPA now periodically polls the EIM if it has any pending packages. Now, a package is not a packet on an IP protocol or something, but it's a logical construct of some packaged operation. And there's two types of operations. The first is the PSMOs, the profile state management operation. And the second one is the EIM configuration operations. So a PSMO is basically profile enable, disable, delete. It changes the state of profiles that are on the EU ICC. And the ECO, the EIM configuration operation, relates to changing parameters of how the EU ICC can contact an EIM. So, for example, when you want to move from one EIM to another EIM, then you need to tell the EU ICC what is the new host name and what's the new certificate for TLS or for the actual signing of the packages, and so on and so on. And to add or remove such EIM configuration, there is the ECO packages, the EIM configuration operation packages. The EU ICCs are provisioned with EIM public keys, so they can verify those packages. That's also new. Let's say you want to do a profile enable on a consumer eSIM, then it's basically a plain text, well, it's binary, but a plain command that gets sent from the LPA to the EU ICC. And there is, again, a plain response. And now the profile enable is actually a cryptographically authenticated command. So the EIM signs such a command, and the EU ICC, because it has the pre-provisioned public key of the EIM, can verify the signature and the authenticity of such an enable command. And then the response also equally is signed again by the EU ICC, and the EIM can verify the signature on that, that actually the profile has been enabled. So what does the EIM do? It's sort of the central management of all these eSIM profiles on your IoT device fleet. In general, it starts all by some business logic adding an operation to the EIM. So there's some non-specified, non-standardized interface by which you, as the owner of a fleet of IoT devices, can basically add or enqueue operations in the database of pending packages for each EU ICC. So you basically tell the EIM, well, I want to enable this or that profile on this or that device. And the EIM then creates a package for this operation, signs that package, puts it in a database. And then when the LPA of that, the IPA of that IoT device polls next time for packages, that package will be transferred to the IoT device. The signature will be verified, it will be executed, and the signed response will be communicated back to the EIM, which can then again notify the external business logic that this profile enable has proceeded. And it acts as a man in the middle for profile download. there's an asterisk at the end because there is another option which we'll talk about later on. But in, I guess, most realistic cases, it will be the man in the middle for the profile download. We look at the download procedure shortly. So this happens all using this eSIPA protocol, the new protocol, a new interface between the EIM and the IPA. It again has interface bindings for ASN1 and for JSON. And once again, the JSON is just base 64 encoded ASN1, so go figure. What's new is that you can transport it over either a CoAP DTLS UDP stack, so a stack that's much more, let's say, resource, much more applicable for resource constrained embedded devices. Or you can transport it over HTTP, over TLS, over TCP, if you have the related protocol stack available. There's also the option for vendor-specific transport. So, for example, you already have some kind of vendor-specific protocol between your IoT device and your backend servers. Then you can just add the transport of eSIPA packages in your custom protocol. And have an EIM that can speak that custom protocol, and likewise the IPA that can speak that custom protocol. So there are is provisioning for proprietary or vendor-specific transport channels here. Yeah. So how does a so-called EIM-assisted profile download look like? Well, first of all, we have the IPA on the device establishing a secure connection with the EIM. So that means your DTLS or HTTPS connection to poll the EIM for any pending packages. And then assuming there is a package pending with a download instruction for this EUICC, then the EIM establishes an ES9 Plus connection to the SMTP Plus. So this means the EIM actually looks like a consumer LPA towards the SMTP Plus. This means the SMTP Plus doesn't even know, it's a consumer SMTP Plus, it doesn't even know whether it's an EIM or whether it's an LPA talking to it. Those speak exactly the same protocol, and it's basically transparent to the SMTP Plus. So anyway, this connection is established. Mutual authentication happens through the entire chain from the EUICC to the SMTP Plus. And then the profile package download happens just like in SGP21 or SGP22. So that's the consumer EUICC with the EIM as sort of a man-in-the-middle proxy there. The man-in-the-middle proxy only terminates the outer transport layer crypto. So the actual signature and encryption of the eSIM profile, the ES8 Plus interface between the SMTP Plus and the EUICC remains intact. So there is no, the EIM is not aware of the plain text of the eSIM profile. It's just the outer transport layer that is proxied, not the inner ES8 Plus layer providing the actual security of the eSIM profile. Now let's look at profile enabling via EIM. Again, we can remember the profile enabling in the consumer eSIM with the local user interface. Now here in this case, it's initiated by the EIM. Of course, previously the EIM somehow from business logic has instructed the EIM over the non-standardized interface that such and such a profile shall be enabled on such and such a device. Then the EIM, whenever the IPA establishes a secure connection, can send this signed profile enable request. The IPA passes that on into the EUICC, and the EUICC then itself can verify the signature because the EUICC has been provisioned with the public key of the EIM during production or later on via an ECO, an EIM configuration operation. And then if the signature verification succeeds, it will disable the currently enabled profile, enable the new profile, generate a profile enabling result, send that back to the IPA. And then we have two cases here. because of course, when the old profile is disabled, and the new profile is enabled, this means the cellular connectivity is lost at that point. And assuming your IoT device has no other cellular or no other internet or whatever network connectivity beyond that one cellular connection of which you have just swapped the eSIM profile, then there can be two outcomes. One, A, that the device can successfully connect to the internet or whatever IP network again, and then send the signed profile enabling result to the EIM. Beyond that, of course, that's unrelated to the IoT UICC. There can be a notification. The notification is a feature that's also available in the consumer eSIM. So if the eSIM profile is configured to generate a notification, that notification gets also sent to the SMTP Plus. So the SMTP Plus is aware that that new profile has been enabled. And if there's a connectivity failure and rollback has been configured, then there's a rollback mechanism by which the IPA can basically tell the EUICC, well, I didn't get IP connectivity for whatever my timeout was. Please roll back, and then the EUICC can switch back to the old profile and then report, that's cut off here in the diagram, report back to the EIM that the profile enable has failed and something went wrong. So you have this is also a strong guarantee in this IoT UICC that you don't have in the consumer system. Because in the consumer system, well, if the user doesn't get connectivity after having enabled a new eSIM profile, the user itself in front of the device can use the user interface to select another eSIM profile. But of course, that's not the case in the IoT case. So you need an automatic rollback mechanism if something goes wrong during the switch to another eSIM profile. The ES8 Plus, ES9 Plus, and ES11 interfaces have not changed. So ES8 Plus is the encrypted eSIM profile download between SMTP Plus and EUICC. The ES9 Plus is the interface of the SMTP Plus now to the EIM instead of the LPA. That's also unmodified. And the ES11 is the one to the SMTS, which I'm ignoring here for the sake of simplification. But what this means is basically that neither the SMTP Plus nor the SMTS know whether a given profile is installed on a consumer UICC or a IoT UICC. The eSIM profiles are the same. They can be ordered the same way. They're downloaded the same way using the same protocol in those two systems. Now, what kind of UICC changes do we have in the SGP32? We basically have an extended ES10X interface. So the X is for A, B, and C. There's 3 different parts of that. And I always ignore what is A, B, and C. It's just ES10 something. What's new is that the UICC needs to store and update the EIM configuration. That means the public key or certificate of the EIM and the host name, where to reach it, and which protocol to reach it, whether it's CoAP or HTTPS or whatever. That all needs to be stored and also then, of course, updated in a secure way. And also it needs support for the verification of those PSMO or ECO package signatures. If an enable, disable, delete, whatever add EIM configuration command or package is received, then the signature must be verified according to the previously stored EIM public key. And execution of packages and return of signed responses, as well as the rollback mechanism, the optional rollback mechanism, or optionally enabled rollback mechanism that we just saw in the previous slide. There is one option that the specs permit, and it's actually the same like in consumer. So in the consumer UICC, already the spec says the LPA could either be on the device, then it's an LPA-D for device, or it can be in the EUICC, then it's an LPA-E. And for the IoT UICC, the same holds true. So the IPA could be on the device, like we described so far. It's called an IPA-D. Or it can be built into the EUICC, then it would be an IPA-E. Of course, embedding all of this in the EUICC requires lots of additional software inside the EUICC. So you need a more powerful EUICC with more flash and more software in there. And also you need to support all the required features in the baseband of your modem that permit actually the EUICC to establish a TCP or UDP connection on the cellular network connectivity. So that's sort of the, but of course, then you don't need any additional software in your device. So that's the advantage of the IPAE scheme. They both have their advantages and disadvantages. So in the IPAE then, if we look at the diagram, the IPA that previously was here above the EUICC, but still in the gray box of the device, that has moved into the EUICC, and now we have the ESIPA interface of the EIM directly going into the EUICC. Likewise, there's another option that we didn't cover so far. That's the so-called indirect download. In this case, the EIM does not act as a man-in-the-middle proxy between the IPA and the SMTP+, but it basically just instructs the IPA to download directly from an SMTP+, which of course only works if your IoT device has public IP connectivity, which for many IoT deployments I would hope is not the case. And it also means that HTTPS support and JSON and all of that needs to be present in the device, which for many constrained IoT devices will also be not very likely. So I think the EIM assisted download will be that we described in the slides will be the normal, the more dominant case that we see deployed. So do we have any Osmocom or open source implementations of all of this? As of today, sadly none. However, at Sysmocom, we have completed an EIM and IPAD development for a customer. And as part of that agreement, it will be released as open source software no later than August next year. So there is some time for exclusivity, and after that, the source code will be released publicly under an open source license of both an EIM and an IPAD. And that is it for the slides.